Hello viewers, in this video we will see the solution to week 4 assignment 4 week 4 assignment 4 for the course digital electronic circuits. Kindly spend time in going through the solutions before or after assignment submission to get better score in the exam. Please subscribe to our channel because we need your support. Kindly share our channel to your classmates, friends and others for their benefit. We'll come to the solution. Let me read the question. How many 2 cross 1 multiplexers are required to generate 256 cross 1 multiplexer? So there is only one multiplexer which has 256 inputs, one output. So for this, how to find the answer? Uh, Stage 1 will have 128 mux. Stage 1 will have 128 mux. Each, sorry, mux, is the mux? Yes, mux. So 128 multiplexers. Each multiplexer will have 2 inputs. So 2 into 128 becomes 256. In the second stage, it has 64. Third stage 32. Fourth stage 16. Fifth stage it is 8. Sixth stage 4. Seventh stage 2. And the last stage it will have, eighth stage it will have only one multiplexer. So if you add all this, you will get 255. So 255 multiplexers are required. Now coming to, otherwise we can do, you can use this formula. N is equal to, where n is the capital N is the number of multiplexers, and 2 power n minus 1, 2 power n minus 1, and this n is the number of mux stages, number of mux stages. And then what is this 2 power n? 2 power n is nothing but number of mux inputs. 2 power n is the number of mux inputs. So therefore, the given 256 you try to express in 2 power 8. 2 power 8 is 2 power 8 is 256. So minus 1 you will get 255. So it is always 2 power n minus 1. That will be that many multiplexes are required if it is 2:1 multiplexer. So the answer is 255. 255, option C. Number of select lines required in the case of 1:8192 demux is. So how to do this one? So you can simply use this formula. So n is equal to log base 2 8192. This 8192 can be expressed in terms of 2 power of 2. So it is 2 power 13 is equivalent to 8192, and this by using logarithm can be expressed as 13 log 2 base 2, and this becomes 13 because log base 2 to base 2 is equal to 1. So the answer is 13. The answer is 13. Or you can also use 2 power 10. Remember, 2 power 10 is 1024, and every 1 bit addition will be multiplied by 2. So 2 power 11 is nothing but 1024 multiplied by 2 will give 2048. 2 power 12 is nothing but 2048 multiplied by 2 is 4096. 2 power 13, so that is nothing but 4096 multiplied by 2 is 8192. So 13. We'll move on to the third question. So the answer is option D, 13. So third question, find the canonical pause expression of y for the given figure. So remember, this is a NOT gate, and this is a AND gate, but there are two bubbles. Here. There are two bubbles here. Let me try. So there are two bubbles here. Okay. Now we'll try to find what is the canonical pause expression. So what is the answer for this one? So what I'll do first? So let me. So they have used AB as select AB or select lines. So there are four variables already they have mentioned here. Four variables AB are used for select lines, and C and D are connected to the input of the multiplexer. So that means four variables are required. So what I'll do first, I'll A B C D four variables I have taken, and then you write all the combinations of these four variables. So that is 0 0 0 triple 0 1 0 0 1 0 0 0 1 1 0 1 double 0. That is each one represents a decimal value 0 1 2 3 4 5 6 up to 15 Okay, so we all know this one, how to write up to 0 to 15 in binary, 0 to 15 in binary. After that, we will see here f, we will see f. So f they have given here. So here if A and B are select lines, we know if A is equal to 0 and B is equal to 0 here, so it will be that will be your y will be connected to I naught, which means C. So that means f equal to C, f is equal to C. So we'll try to find output, we'll try to write the output first now. So A equal to, now A and B 0 0 0 0 0 0 0 0 in both, in first four. So f is equal to C, f is equal to C, just now we saw, because f y sorry f is connected to y naught, and this y naught is nothing but C. So therefore this is I naught. So therefore f equal to I naught is equal to C. I naught is equal to C. So now what I'll do here, after writing A B C D all the input combinations, so f is equal to C. Therefore here C is 0, f is 0. C is 0, f is 0. C is 1, f is 1. Here C is 1, f is 1. That is nothing but f equal to 0. That is nothing but f equal to 0. Next, what I will do here, you can see here, this is AB. Again, AB combination is, this is 0, this is 1. Okay. So now we will see here next four combinations. A and B 0 1 0 1 0 1 0 1. So in that case what will happen, 0 1 0 0 1, what will happen, this f will be connected to I1. But what is I1? So I1 is connected to D. I1 is nothing but D. So therefore I1 is nothing but D. So simply what I will write here is 0 0 1 1 0 0 1 1. So next we'll see here 1 0 1 0 1 0 1 0. So now what about I2, this diagram? So f will be connected to I2. F is connected to I2, but what is I2? I2 is coming from a NOT gate. What is the NOT gate input? NOT gate input is C. This is C here. Input of NOT gate is C here. Output of NOT gate is C bar. Therefore, I2 is equal to C bar. That is nothing but F. So F is equal to C bar, because I2 is equal to C bar. So now what we will do? Whatever C is there, the F is complement of C. So C is 0, F is 1. C is 0, F is 1. C is 1 here, F is complement of this 0. C is 1, F is 0. So next 1 1 1 1 1 1. So next last four combinations 1 1 1 1 1 1 1 1 for A and B. So next here you can see here for 1 1, both 1 1, this Y, Y or F will be connected to the I3. What is I3 here? I3 is nothing but input is C bar. Bubble is there. Here also bubble is there. So C bar and D bar. The output is C bar D bar. So you can see here I3 is nothing but C bar D bar. It is an AND gate, but two bubbles are there, C bar D bar. So now this can be represented as C plus D whole bar by De Morgan's theorem. So this is simply nothing but a NOR gate. So therefore we know if both are 0 0, if C and D, C is 0, D is 0, 0 plus 0 is 0 complement. So 0 and 0 NOR gate. So 0 0 input, NOR gate output is 1. If 0 for 0 1 combination, NOR gate and for the remaining 0 1 1 0 1 1, NOR gate output will be all 0 0 and 0. Now the thing is, we have to identify the output f is equal to, y, it should be actually y, or f. Okay, so this f, we have to consider only the terms which are for f equal to 0. So this is 0. For serial number 2, serial number 0, it is 0. Serial number 1 output is 0. Serial number 4 output is 0. Serial number 6 output is 0. Serial number 10, serial number 10 output is 0. Serial number 11 output is 0. Serial number 13 output is equal to 0. Serial number 14 output is 0. Serial number 15 output is equal to 0. So therefore 0 1 4 6 10 11 13 14 15, option A. So what we have taken here? 0 1 4 6 10 11 13 14 15. So output 0, only that serial number or decimal number is considered. Option A. Option A. 0 1 4 6 10. So 0 1 4 6 10 11 13 14 15, option A. Ours is option A. Okay, we'll move on to the next one. Fourth problem. Fourth, so they are asking for the total delay. They are asking for the total delay. So total delay will be here. We'll calculate the total delay here. How to calculate this one? So here we have, oh, 1 second. So NOR gate. So NOR gate. So first multiplexer, NOR gate, and then inverter. So multiplexer is 1.5. NOR gate is having the maximum delay. NOR gate is having the maximum delay, and the least delay is the NOT gate. And the multiplexer is having 1.5 nanosecond delay. Okay. Now there will be delay of this one. We'll see here. Solution. We'll see here. So 2 mux are there, 2 NOR gates are there. So here propagation delay is equal to delay from NOR gate 1, delay from NOR gate 1. So delay from, this is NOR gate 1, plus delay from mux 1. So delay from, this is multiplexer 1. Then delay from NOR gate 2, delay from NOR gate 2, then delay from mux 2, delay from mux 2. So what is the answer now? So delay from NOR gate is 2, delay from mux is 1.5, delay from another NOR gate is again 2, delay from another mux is 1.5. So you will get 7. You will get 7. This is 1.5 plus 1.5 is 3, and 2 plus 2 is 4. You will get 7 nanoseconds. So answer is 7 nanoseconds. 7 nanoseconds. Option D. We'll move on to the fifth one. So fifth one, 74154, 74154. So just remember, to enable 74154, this strobe input must be 0. Strobe input must be 0 to enable this particular IC 74154. Here also 74154. If strobe is 1, this particular IC is not enabled. Okay. Now we can see in here, if A is equal to 0, if A is 0, so this is directly given to the strobe. This is enabled. The first 74154 is enabled, whereas for this one the strobe is coming through NOT gate. So NOT gate output is 1, and therefore this is not enabled. This is not. So second IC is not enabled. That is a simple thing here. We will see here. What is 74154? 74154 is 1 to 16 demux. That means 1 input, 16 outputs it will have. So if A is equal to 0, now what is the question they are asking? If A is equal to 0, so definitely if A is equal to 0, only first mux is enabled. This is not enabled. So we now concentrate only on the first mux. So if A is equal to 0, demultiplexer 1 is selected or enabled, demultiplexer 2 is not enabled, so we will not concentrate on this second mux. Okay, now coming to this first mux. So if b is equal to c equal to 0, question, if b is equal to c is equal to 0, here what will happen? So what will happen, that will see, if b is equal to c is equal to 0, then so we know that each multiplexer is 1 is to 16 demux. Now it will now act as 1 is to 4 multiplexer, 4 demultiplexer, because c is equal to b equal to c equal to 0, because b equal to c equal to 0. Now it will and only will have, see here, now only will have d and d, now will have only d and e as the inputs, as the combination selection, as the selection line. So therefore the outputs 1 is to 4 multiplexer with the outputs y0 to y3, it is not y4, y0 to y3. So the answer is option A. So I'll repeat here. So if A is equal to 0, only first multiplexer is selected or enabled, and second multiplexer is not enabled. In first multiplexer, if B and C both are 0 0, then that will act as 1 is to 4 demultiplexer, not 1 is to 4. Okay, and therefore automatically it is y0 to y3 outputs. So the answer is 1 is to 4, this one, option A. This is not y4, this is y3. We'll move on to the sixth one. So determine the inputs of 4 is to 1 multiplexer to make the output. So they are given output Q equal to A plus B plus C. So we'll see here, A is the MSB and C is the LSB. So okay, we'll see now. Okay, now A, B, C, A is MSB, C is LSB. Okay, so what we'll do here, because it is a 3 variable, it is a 3 variable, it is a 3 variable, is a 3 variable. Okay, it is a 3 variable. So A, B, C, it is a 3 variable A, B, C. So A, B, C. Therefore, first you write down all the input combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and then 1 1 1. Then what is Q here? Q is nothing but A plus B plus C. So 0 plus 0 plus 0 is 0, 0 plus 0 plus 1 is 1, 0 plus 1 plus 1 is 1, 0 plus 1 plus 1 is 1, because this is an OR operation, not an addition operation. Remember, it is an OR operation, not addition. 1 plus 1 is 1. So 1 plus 0 is 1. Again 1 plus 0 plus 1 is again 1. So for all other combination, remaining combination, it is 1 1. Okay. So therefore, first we have written the output for Q, and then we'll see here what they have mentioned here. A and B as select lines. A and B are now select lines. So 0 0 0 0. So what is the D naught input? So D naught input here is equal to C, because the output here is 0. If it is 0, this is 0. If this is 1, this is 1. Therefore D naught is equal to C input. Similarly for this one, 0 1 and 0 1 select lines. So what about both are 1 1? Both are 1 1. So D1 equal to 1 1. And for 1 0 1 0, this is D2 equal to 1, because both are 1 1. And for 1 1 1 1 combination, D3 is also equal to 1 1, because both are 1 1. So answer is option A. Answer is option A. Option A. So D naught equal to C, D1 equal to 1, D2 equal to 1, D3 equal to 1. We saw here D naught equal to C, D1, D2, D3 are all 1 1 1. So next one, seventh one, which of the following statements are not true? For more than 2 input XNOR gate, output is 1 if there are odd number of ones at the input. Let us see that one first. So I have taken a single XNOR get with multiple inputs, but the number of input number of ones is odd. The number of ones is odd. So now what is this one? X 1 exclusive 0 exclusive 0 exclusive 0. That is the thing I have written here, but it is bar. It is bar. It is a bar not operation. XNOR operation. Okay. Now for XNOR, if both inputs are 0 0 or 1 1, output will be 1. Output will be 1. Remember, if both inputs for XNOR is 0 and 0, or if both inputs are 1 and 1, the XNOR output will be 1. Now we will see here for this particular input combination 0 and 0, so output will be 1. It is XNOR operation. Okay, not it is an XNOR 1. Okay, and then this one with this 0, so it will be 0 here because both are not equal, therefore it will be 0 here. Now coming to the last bit, again 1 and 0, again these two are not equal. If it is equal, it will be 1. If they are not equal, it will be 0. So therefore first answer is wrong. So first answer is wrong, and similarly parity generation and checking involve single bit XOR get is also false. So 1 and 3 are not true. 1 and 3 are not true. 1 and 3 are not true. So 1 and 3. Option D. And we'll move on to the 8th one. So before that one, we'll continue this in the part 2.